as we have seen, verification is checking that we have solved our mathematical model correctly, that we have input the right mathematical model into the tool, and the numerical errors introduced by the tool are acceptable. And here we are assuming that the coding in the tool is right, and I think that's a fair assumption with a widely used tool like ANSYS Fluent. First thing is to do sanity checks, and we checked the trends in velocity and pressure against expected trends. So I think we did a fair bit of that. Next thing to look at is, does the CFD solution honor the boundary conditions in the mathematical model? And we did some quick checks on the boundary conditions on velocity and pressure when we were looking at the contours, and we also looked at the boundary condition on the turbulent kinetic energy at the inlet. So I think we can be fairly confident that we have input the right boundary conditions into the tool. One thing to keep in mind is that we input guess values of k and epsilon at the boundary. So we have k and epsilon where guess values, and we need to vary that and check that it doesn't affect the solution. So that's a check one needs to do on the boundary conditions. And I expect that it won't affect the solution very much, because we saw that the turbulent kinetic energy was being dissipated, the turbulent kinetic energy that we put in, and then it was being generated in the regions near the airfoil. And then the other thing to check is, does the CFD solution honor the physical principles in the mathematical model? And the physical principles are mass and momentum conservation in the domain. Mass conservation is straightforward, as we've seen in the pipe flow example. So I went and checked for my own results, and I got a net mass imbalance of the order of 10 to the power of minus 7, which is a small fraction of the incoming mass flow rate. So, and make sure that you check this in Fluent, and this is a check that you should do for all CFD case studies. So you can exit out of CFD post, bring up Fluent, and do this check. So I've done that. The momentum conservation check is not as straightforward to do, so I'll put a question mark there. Ideally, one would do it, and one can write expressions in CFD post and do it. So I'll put a question mark there. It's recommended, but it can be a lot of work. Moving on to the numerical errors introduced by the tool, is the linearization error acceptable? We got the residuals down to of the order of 10 to the power of minus 6. We had a little bit of an issue with the k and epsilon residuals, and we also checked that the drag coefficient and the lift coefficient are not changing. So I think we can be fairly confident that the linearization error is not very large for this case. It might become a problem when you change the mesh. Is the discretization error acceptable? One thing we did was when in the discretization, we are not going out to infinity. We have put our far field boundaries at a finite distance, and we need to check the effect of moving that far field. And this is a check one needs to do for every external flow. It's something that is easy to overlook, and I've seen students getting very unphysical results because they put their boundaries too close to the object. If you look at the NASA website and look at their meshes, they go out to 500 chord lengths, and we have gone up to only 12.5 chord lengths. So moving the far field boundaries, checking the effect of the far field boundaries is something that one needs to do. And then of course there is mesh refinement that has a huge effect on the discretization error. We saw that we had poorly shaped elements at the trailing edge. So we need to try to fix that. This can be very time consuming, as my teaching assistants would tell you. And also the near wall. We saw that we just had one cell across the turbulent boundary layer. So that's a problem. So the near wall mesh. And in fact, in turbulence, you have to know what the near wall treatment is, and there's something called Y plus, and you have to check the Y plus, and I'll talk about that because that's an important consideration. So these won't affect the pressure distribution, and it won't affect the lift, but these will have a huge impact on the drag coefficient. So this is something very important to do, but also with the recognition that it can be very time consuming. And then you can get convergence problems, your linearization error balloons. So those are some key checks one can do on the numerical error. And then finally, does the CFD solution match hand calculations? And the hand calculation we had was from thin airfoil theory. It said the lift coefficient should be of the order of 1.1, which was the case in our results. So I think we had at least one hand calculation to check against. And of course, we also had the sanity checks. So those are some verification checks that we can do. And in this case, we also have validation. So I'll talk about that also.